Når det? Kan du faktisk klare å gjøre den?
Maybe I can quickly come back on these things I mentioned yesterday, because it's just not bad to understand what's happening there, because these constructions here that are used in many different things as soon as you do numerics in the computer. So if we forget this a little bit for a second, you can imagine simply that you have some variables y and x in a function like this, and you would imagine that x is a parameter in that function, so that's something that is given, and y is something you have to solve the function for. And typically you would deploy Newton on y to find its value. And then, so if you were to change the parameter x, y would change accordingly, so Newton would take a few steps to get c equals 0. So in that sense, you could think of y as a function of x. You could really think that it's essentially y is a function of x via this set of constraints. But chances are you will never be able to write this thing like, as expressions like sine and cos of whatever, because this may be a set of nonlinear equations that you cannot solve on pen and paper. So this function, you can evaluate it via applying Newton on this, but you may not be able to pin expressions on that. And then the question we ask is, can we differentiate that function? And if we can, what is the value of that derivative? So that's really what's going on here when we try to do del theta, del x. So x would be these parameters, and the theta is my y in that sense. And this answer turns out to have a very simple answer. If you think of your y as a function of x, you could think essentially that this will hold for any x. So if you change the x, the y will change accordingly, so that this function remains 0. It's kind of the definition of how y is moving according to x. And if this is true for every x, you could really think of your c as essentially being flat over x, right? So for any value of x, y will always adjust to keep c at 0. So essentially c is a flat function of x. So if you do a total derivative of c with respect to x, this should be 0, right? Because the function is never moving. And if you unpack this, it's then just a chain rule. That's del c del y del x plus del c del x equals 0. And that's how we got these statements here. And then you can invert that as soon as this guy is full rank. You can basically write del y del x as a function of the rest. So that's fairly simple mathematics to get the sensitivities out of these implicit functions. Okay about that? So whenever you have variables implicitly defined by some constraints, remember that under some simple conditions you can actually differentiate these variables defined by the constraints, and that's very useful in many contexts. You can also go to higher derivatives, but it's becoming messy a bit quickly. Okay, any question about yesterday also before we move on? I'll release a few things at the lunch break. I'll use some codes and some new exercises for those who would want to try something. I think I'll just do this just so that you know what's behind these words, because it's actually quite commonly used in optimal control and some other things, so it's good to have a vague idea of what's happening there. and I guess I'll skip that one. It's about second order sensitivity, so how you compute the Lagrange, the Hessian of Lagrange function. But it's based on that. So once you understand that, you're close to understanding that. Okay. We can think now a bit more abstractly than before. You would recognize this looks a lot like an integration code, depending on what this function is. For example, if you use Euler, this function would be s plus delta tf, right? But this can be any arbitrary function. It could actually be a complete RK4 scheme, for example. It's just basically a function that updates s from S and U, so something that's kind of wraps on its own. So if we think about any algorithm that takes this form, so like evaluating a function on the variable a number of times, then we ask what happens when we differentiate this algorithm. And we have seen together what we call forward sensitivities, when we basically unroll this replacement, and we pass it through matrices like this, the A and B's, and that gives you the sensitivities of the algorithm with respect to X and U, right? So, but that's something you can do for your integrator. That should be the same letter here. That's a typo. So that's what you do for an integrator, but that works for any function that does this replacement over time. And we call this forward sensitivities because the sensitivities are basically built together with the simulation going forward in time. So this I going from I to N, you can think of them as time steps moving forward in the simulation. If you look a little bit of the complexity of doing that, so what does it mean in the computer to carry these matrices A and B? Well, it's just about essentially unpacking how large these matrices are and how much operations we are doing in these lines of code. So without the sensitivities, I would not have these guys, and I'm assessing what is the cost of evaluating these things on top. And if you consider that you have n states and m inputs, for example, if you talk about simulations, these matrices are typically dense, so there's no zeros in there. And storing them, it's n times, so n squared for A and n times m for B. They are floating numbers, so that's the memory footprint you have. All these multiplications here, these are matrices. So when you form these lines, these are matrix multiplications. It's actually a fairly expensive operation, a matrix multiplication dense. You basically have a complexity of n cube on these two operations. And you do this capital N times. That's for A, and for B you have n squared m. This addition is typically not very expensive. That's a much lower complexity, but the multiplications are quite expensive. So if you sum all this, you end up with this kind of complexity. So n dominated by n cube and n squared m. So you can think if you have, if you double the number of states in your system, you increase the computational time you need to form this by 8, right? It's cubic complexity. So the cost of doing these things increases very quickly for larger systems. So that's a bit bad news. So these forward sensitivities on explicit integration codes, they are actually quite expensive. And you see that for really in practice, simulating a system is typically fast. Simulating with forward sensitivities, that's slower. You see that you have more operations to do. Now, the question behind joint mode sensitivities is you can imagine that you care only about, you don't care about getting del f del x and del f del u for some reasons that I can explain a bit later. We don't care so much about these guys. We care about scalar functions of these guys. For example, something like this. So you have some function that maps Rn to R, and you will essentially evaluate a function over these guys and then you want to differentiate that function with respect to x as opposed to the full f. One example could be if you have in your OCP, you could imagine that your cost is essentially your simulation at the end. Well, let's read it that way. There will be a terminal cost on your endpoint, and this is a scalar function. So in that sense, if you would want to differentiate this cost function with respect to all the variables, you're essentially asking what is the derivative of this scalar cost function of the simulation, but you don't care about the derivative of the simulation itself. You see what I mean here? Yeah. So you basically don't care about del f del x, but about what happens to this function over f, which would be scalar. The adjoint mode AD, or reverse mode, sometimes it's called that way, would do something different when you care about here not the end of the simulation, but some function of that end of the simulation. So your code now, you could think of it as taking states and inputs, running the simulation, but at the end, instead of returning the complete simulation, you only care about this scalar function evaluated on your simulation, for example, a cost. And you return essentially this capital T of xu. So it's function of the inputs you provide in your code. That would be an x actually here. And so you evaluate that. And you want the sensitivities of T with respect to xu. And if you have this situation like this, it's a lot cheaper to compute the sensitivities. And the reverse mode will essentially compute the sensitivities not forward in time, but backward. That's what often happens when you form adjoints in optimal control. And it's quite simple. So what you would do is you would look at this final cost or final function, this zeta of Sn, and you wonder what is the sensitivity of this guy at final time n with respect to the state at any time in the loop, so one of the SIs. And you would call this thing lambda I. And you have to imagine that this is a vector now, because this zeta function is a scalar. So when you take the derivative, it's a vector. So you call it lambda. The lambda n, the terminal lambda, is this function here. And this is something you can know because the function of this is basically the direct function of Jacobian of this function. So del zeta, del its arguments that you would evaluate on your simulation. And now you have to pin some kind of dynamics on this lambda, or discrete dynamics, and that's just about chain rule. So if you have the del lambda I, you can build the previous one. So this is by definition this guy, and then you apply a chain rule. So del s n del si minus 1, you go del sn del si del si del si minus 1. So that's your lambda I by definition, and that's essentially associated to the dynamics. So this guy is differentiating that function essentially, this update rule. You can do a similar construction for when you differentiate with respect to the inputs. It's a little bit trickier, but it's also just essentially chain ruling things in a smart way in your dynamics. So bottom line is that if you want to build the sensitivity of this T function, the output of the code, you need to evaluate these lambdas, and essentially that gives you the answer directly. So the lambda 0 is del t del x, and the del t del u is made of a combination of the lambda i's. And the lambdas are defined by these recursions. And so The idea essentially would be, obviously it's not obvious. You may not see all the details, so if you are interested in what's happening here, go back in the slide. But essentially it's just a chain rule, and we have just defined the sensitivities starting from the end, and we go back into our simulations with these lambdas all the way to 0, where we started the simulation, and that gives us the sensitivities of this function. So the way you use that, you do a so-called forward pass that's just evaluating this. It's a forward simulation. You compute the S's and you store them, all this S0 to Sn. So now instead of just doing replacement, you store this complete chain of states. You store all the points on your trajectory. And then when you're done with that, you do a backward or reverse pass where you actually start from n or n minus 1 and you move back in time in order to compute your lambdas. And you can compute your sigmas here to support this sum essentially. And yeah, you can make some efficient memory usage by not storing all the lambdas, but just making replacements. And then you just run this code backward, and that gives you your del t del x, del t del u. So you have a forward pass, backward pass, and then you get the sensitivities of this t function. So forward, backward, you need to store the trajectories on the forward step. So there is a bit of memory footprint, but that's n times n. This is quite inexpensive. It's just a simulation, so it's not. That's typically cheap. The backwards pass or sweep, sometimes it's called. You have also matrix, but matrix vector multiplication. That's less expensive than matrix. That's in complexity n square for each step here, and p was the number of parameters somewhere. I don't remember what my p is. But okay, bottom line, the total complexity of doing this is n times less expensive than the forward mode. So instead of having n cubed in the complexity, you have n square, which can be much better if you have large systems. Yeah. So when with good AD codes, you don't have to think about these things yourself. Like for example, Casadi would be selecting an adjoint mode on your integrator if it sees that this is what you need. So it will analyze what you're doing, and if it realizes that you're just asking the derivative of a scalar function over an integration like code, it would actually automatically select a reverse mode on your function. Maybe I can just start this one. I will not finish it, just to show you where this is used mostly. Because adjoint mode is essentially designed to differentiate scalar functions. Your Lagrange function is a scalar function of the dynamics, and that's one reason for using the adjoint mode. You'll be able to form the gradient of the Lagrange function using the reverse mode, and then you'd form the Hessian by doing a forward mode over the reverse mode. So I'll not detail that too much, but just to point a few things here. So this would be an NLP coming from multiple shooting with your shooting gaps here, initial conditions, your variables. And so remember, then you would, for example, throw an SQP at this problem where you will solve these QPs, and B should be ideally the exact Hessian of your Lagrange function and maybe an approximation of that. So if you can do that, you'll have very good convergence typically. And the question is, how do you compute this guy if you wanted to? And just as a reminder, we saw that before. Huh? So this Lagrange function would essentially be a sum of scalar products between lambda variables and all this shooting gap constraints, and also something on the on the initial conditions. Yeah, maybe just a remark. I didn't say that yet. It may be obvious, but maybe not. Any constraint that is linear or affine in your problem will not appear in the Hessian of the Lagrange function. It's kind of obvious if you, for example, take this constraint here. That's the constraint on the initial conditions. It's linear or affine at least in the variables. If you differentiate this guy twice, it disappears. Right? So any linear constraint will not have any impact on the Hessian. Only the nonlinear constraint, possibly these guys, will enter the Hessian and matter in your SQP. Okay, so if you take the second order derivative of this Lagrange function with respect to the variables, for example, a wk, so that will be a pair of xk and uk. So we'll take the Hessian of the cost, obviously, and that's typically cheap, especially if you have a stage-wise cost. And then you'll sum up the contribution of actually this scalar product alone. Again, this guy here, it's linear in xk plus 1. So if you take the Hessian of that thing here, it will disappear. So only this contribution remains. So essentially, when you form the exact Hessian, you will have to form the Hessian of this scalar product. So lambda transpose times the simulation on some shooting interval. Yeah, it's sometimes called directional Hessian because you essentially take this vector function and essentially prompt it in a specific direction, lambda, via this scalar product, and then take the Hessian of that. Yeah, I'll stop there, but essentially what is happening if you want second order sensitivities is that you need to evaluate the Hessian over this scalar product, where f is a simulation and mu plays the role of your lambda, if you want, in the NLP, and that's a different lambda than the one you would carry in your adjoint mode sensitivities. But then essentially you end up doing a forward pass to get the S, a reverse mode pass to get the lambdas, and then a forward pass again over the adjoint. So you can look at this offline. But what happens if you want to compute the Hessian of the Lagrange function is that you will have, that's the cheapest way of doing it typically, that you do the simulations, then there's a backward pass on your simulation, and then a forward pass with sensitivities on these things, and you get the Hessian of your simulation. And you can probably guess that's not cheap. You go 3 times through your simulation on each of your intervals, so that's actually expensive. And again, like softwares like Casady, they would do these things for you typically. But they will do it in the background. Okay, there are some interesting remarks here, but it's going a bit too far into the details. Any question on that? Okay. So yesterday we saw shooting methods. So that was essentially, we discussed these 2 boxes, how you transform an OCP into an NLP. This guy, so single shooting is not used so much, I would say, for the reasons we saw yesterday. In most cases, it will not run faster in your computer. And in some cases, it will make the convergence much more difficult. So by default, people tend to use multiple shooting. But you have a competitor, in some sense, to multiple shooting. That's so-called direct collocation. So one of the very common approach for solving optimal control problems. There's an interesting thing here. So these 2 things look different in some ways, and there are obvious connections as well if you frame them in the right way. And it's actually only last year actually that we published a paper showing the equivalence between these two things. So at the end of the day, you can make them totally equivalent, but it was not obvious in the first place. Yeah, okay. So I'll describe a bit what is behind this this box. And so yesterday we saw collocation-based integrators, and I can go back to this essentially because this is the main idea behind direct collocation. So we'll be deploying this collocation-based integrators as if it was multiple shooting, but in a different way. So we'll see what that means. Okay, so I'll take a bit more time to go through this polynomial way of building the dynamics and see a bit what happens in there. Okay, so we go back to this picture. That's the picture from multiple shooting. You have this x, k variables inside your NLP. Your NLP can move these dots, and then you will build these simulations, these little tails. You have constraints to close the gaps. So that's the picture. And then you would think that essentially you want to build all these simulations so we can zoom on one. And what we saw in collocation, what happens is that you would create a new time grid in the interval. For example, why not this point? So I'm here between tk equals 1 to tk plus 1 equals 2, and I select some points. I'll tell you in a bit what these points are, or how you select them at least. As you can see, they are not uniformly spaced. I said that yesterday already, and that's not for random reasons. You actually should choose them in a good way. Here I chose essentially 4 points plus tk. That's one specific choice of grid. So I have my capital K equals 4. So I'll build a polynomial for 4 here. You can actually select how many of these time points you want to choose. You can take larger or smaller numbers. I didn't tell you yesterday how you build this polynomial. So if you remember this family of polynomials that you will combine to form the trajectory. So there are Lagrange polynomials, and if you remember, they are basically built so that they go through the thetas that we select to support the interpolation. So you can build them by doing that essentially. On each, you take all your time points. These are given essentially. It's in this list. And you do t minus tkj over this denominator, and you do a product of all these things, and you just omit the indices that would create a 0 on the denominator. So you have a family of them for I going from 0 to k, which will change this guy here and change the j you omit here, so you get a family of polynomials. And so they have this property that we saw already briefly yesterday. Each of these polynomials, they go through zeros on all the time points but 1, and one of them they go through 1. It's easier to see that visually. The first of this polynomial for I equals 0 will take a 1 on these checkpoints, so tk 0, and then pass by 0 everywhere else here on all the checkpoints. And the second one, same story. Passes by 0 everywhere, but on this checkpoint here, and so on and so forth. So it just happens by construction, by doing this thing here. Right, so that's we saw this graph yesterday already very quickly. That was what I was trying to show. And then, so you build your interpolation. So that will be your simulation in the end with these theta parameters by basically doing linear combinations of these guys. So these are parameters you will use to simulate your system, to basically fix what the trajectory should look like on the little tails. and this will be the polynomials. If you think for a second, because of this property up here, this will mean that this interpolation here, it's essentially a curve in time, but on the specific checkpoints, it will actually go through the parameters we choose, just because on a TKJ, these polynomials, they will be all 0 but 1, and the one that matches theta kj. So what really happens in the end is that, we briefly saw that yesterday, these thetas, they are kind of sliders on a mixing table that will move around the curve S. So if you, for example, move one of these points or another one, you'll basically reshape the S accordingly. They have an extra property that is very good for interpolation. That's these polynomials are orthogonal on this time interval, i.e. Their scalar product are 0. It's going a bit deeper, but it has some useful properties when you want to interpolate with such things. Okay with that? Yeah.
Why on the previous one it shows like between 0 and 1?
So the previous graph, this one?
Yeah. So it's like the next graph, the linear combination of this graph?
Exactly. So this would be all these polynomials, this p, k, i's, I going from 0 to k. Right. And then theta is just a set of parameters I can arbitrarily choose. And if I do these linear combinations, I get this, right?
And you choose like 1 in the previous graph? You could have chosen kind of theta and then...
So when I show this, I actually chose all these theta. So I chose these five numbers. And so you choose 5 numbers, you assemble this for all time t, and that's this blue curve here. And what I'm showing next is what happens if I change one of these numbers. So these bubbles here, they are the thetas really. And I can use them as parameters to reshape my polynomial. But these rounds here, they don't correspond to these rounds here, if that's what puzzles you or confuses you.
But they correspond in like the circles there multiplied by theta, are the circles there?
Yeah, so my first theta is 0.5 something here. My second theta is 0.9, I guess. 1.2 probably, and so on and so forth, right?
Yeah, so if you made like a previous graph with these circles.
But the previous graph is showing all the p's. So there are all these polynomials, and they are fixed. Huh? It's just, you take this polynomial here, and evaluate it for a t going from 1 to 2. For I 0, you get this first curve here. And it just goes through 1 on this first checkpoint. But I cannot move this guy. It's fixed by this construction. But once I combine them using these weights, if you want, these thetas, then I get a single curve, because I sum up all the polynomials. And it turns out that these weights will essentially be checkpoints through which the curve has to go. It's not yet convincing, or yeah.
And that is because they are Lagrange polynomials.
Yes, yeah, exactly. If you select that differently, then you would have something completely different.
Is there any reason to choose apart from this Lagrange polynomials?
So yeah, one of the reasons has to do with this property here. Yeah, the orthogonality. And if you go really far into the theory of integration and quadrature, these guys have strong properties in terms of how accurate this interpolation will be. But they're also convenient in terms of conditioning. For example, if you were to interpolate something using a polynomial, you could just say, "Oh, I'm gonna go for this," for example, right? That sounds reasonable. The only problem is that if you were to imagine that, I don't know, t is between 3 and 4, why not? And you use a fairly high order, maybe up to 8, for example, then you start talking about 4 to the 8, right? On the last time point. So some of your thetas will have a massive influence on the polynomial and some not so much. Here you have a kind of even impact of the thetas on the polynomial, so that's convenient. Also, simply in the construction that we will do later with this, it's very convenient to also have that the polynomials just go through these points, because it will reduce all these guys here to just the parameters themselves, as opposed to a linear combination of the polynomials. Okay, I hope it's somewhat clear. I understand it's not trivial, but yeah. Okay, so this is essentially just a curve builder, right? I have a technique now to build a curve that goes through these points. And I can select these points the way I want. And of course, what we will do next is select these points such that this curve here is a close approximation of the dynamics of the system. So that's where collocation-based integration pops in. So back to this picture again. So we discussed that a little bit yesterday, but it's good probably to repeat that to digest a little bit. So in that context, so that's your multiple shooting picture, you would think of this S of these interpolations as these tails here. So on each of this interval, you will put a polynomial that tries to approximate this guy as well as possible, and that guy, and that guy. So on each of these time intervals, you have one of this interpolation. So if we zoom on one, we also saw that yesterday. So it looks like this. Actually, if the time interval is fairly short, it's quite common that the trajectory is a bit uneventful in some sense. It's actually kind of almost linear. You also see with this property that for very short integration times, the trajectories are fairly mild. So you put this time grid, so that's something you selected. You also select the number of points you want. Here it's 4 plus the first one. And then you pin this construction on it. So again, that's this blue curve we saw before. And these checkpoints are basically pinning this curve at specific instances. So the polynomial has to go through these bubbles. And again, so this would be a number. If I slide this guy around, it will reshape the polynomial so that it goes through the point. Same if I move this one, it will reshape the polynomial. Just as a warning, so it's not obvious in that picture. So this guy is one of my states. I may have a number of states. So for each state, I have thetas that will define how that state is moving. Is that clear? So if you think of a 4-state system like the pendulum we saw yesterday, I have 4 of these curves. And I have 4 thetas, but I use all the same polynomials. But maybe that's just to, maybe it's a bit too early to say that, but you have to imagine that you have these theta ki's. You have one theta for each state. So essentially this theta ki is actually a vector, such that S is a vector, right? And now you see that if you were to go down to coding these things, you would have this. So theta ki is in Rn, n being the number of states. And the theta for one state would be, in some sense, theta ki j if you want, right? So actually, your thetas are a tensor, and that's a bit nasty to store in the computer. So if you play with coding these things, you would realize that this is not completely trivial. But mathematically, it's easy. You have your thetas; they generate these trajectories. And I will adjust these thetas such that this blue curve here is a good approximation of your ODE. Okay, so these thetas, we have k plus 1 of them for each state and for each interval. So you can count, I chose k equals 4 and I have 5 of these dots, 4 on these points plus the first one. Okay. And so again, we saw that yesterday, but the way collocation works for doing this, you will basically bring this first points on the initial conditions. That would make sense that the polynomial starts here. So this theta k0, it should be xk. And that, of course, corresponds to your interpolation at time tk. And then, again, you want that the slope of the polynomial on each of these checkpoints is such that the ODE is solved. So if you think about that, it would look like this. So the del of del t of your interpolation at time tkj, so that's one of the checkpoints, must equal f of the value of the polynomial at this point, comma uk. So that's x dots as approximated by the polynomial, and that's x as approximated by the polynomials on these different checkpoints. So you'll write one set of equation like this for each of the j's going from 1 to k, right? So I impose one constraint on the first point and one constraint on each of these points. So I end up with k plus 1 constraints for k plus 1 degrees of freedom. So that will basically define my thetas. Yep.
Why? No.
No? Yeah? Should ask questions. This is not obvious. It's a bit of around the corner construction. Yeah.
So you get that the derivatives of polynomial equals sort of
the dynamics.
Yeah.
Yeah.
But in between, you just then have that at these points is equals, and then just the area under the curve dynamics are equal, or are they equal?
Yeah. So that's a very good question. What happens in between? So in between, the OD is not satisfied. And that's what you have to live with because you have a finite parameterization. I'll talk about the order of accuracy you get in the end with these techniques. It turns out to be very high, but yeah, that's yeah.
So more in terms of like Gauss quadratures and so forth.
It is a Gauss quadrature. It's completely based on that. Yeah.
Yeah, but
Yeah.
then you sort of make something very different, most likely just at the lot points.
Yeah.
Is equal, and then you just
Yeah, it could be a lot of things in between. And actually, from a very intuitive point of view, you can kind of see what's happening or what's going to happen here. Imagine that the true trajectory is this black thingy here. I mean, it's obviously trivial to pass a polynomials through that, and you'll be very accurate everywhere. If my trajectory was doing something crazy, that would be pretty hard to nail that with a polynomial. So bottom line, things go well if your time intervals, the tk plus 1, are short enough that the trajectories are a little bit uneventful or easy to catch with a polynomial of not crazy high order. Essentially that. So it all boils down to having a delta t that is not too large. Yeah.
How do you choose the time intervals between or in the simulation?
The tk plus 1?
The tk, comma 1, comma
Okay.
2, so the time intervals between those.
Yeah, this time grid here.
Yeah.
Yeah, I'll mention in a slide how you choose them. There are actually very, very strict rules on how you should choose them. So, in principle, you could choose anything you want.
Yeah.
The problem is that the order of accuracy you'll get in the simulation will be high only if you choose them along a very specific rules. And that's actually related to Gauss quadrature. That's what is giving you these time points. They turn out to be the roots of polynomials themselves. But yeah. Explaining exactly how it works is quite involved. I looked at some point if I could explain that in lectures, but I think it's a bit too far. Yeah, so remember this x, k, uk, they are variables coming from the NLP. So they are basically like inputs in these constraints that are fixed. And then you will resolve these constraints in theta to get your integration. Yeah. this thing here, because of the features of the Lagrange polynomial, that's actually theta kj. It's basically the bubble itself, so you can replace it like this. And this guy here, again, it's just an interpolation, so when you time differentiate it, it's just about time differentiating the polynomial. And remember, this guy is really just a polynomial in t, it's nothing else, so time differentiating it with respect to t is trivial. You just go down 1 degree and change the coefficients. Yeah, so that's how the what the collocation constraints look like. What time is it? Should we take a break? Here, yeah.